Good evening, everyone. I'm Anesh Shambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bangalore. Welcome to today's live weekly interaction for the NPTEL course, Dynamic Behavior of Materials. The course code is NOC24ME102, and this is the fourth week. We'll be covering content related to that. The outline of today's session is as follows. In this week, we learned initially about the plastic waves and uniaxial stress. For this, I'll draw a diagram referring back to the one carbon duet setup, which goes like this. You have a long thin rod, a weight being suspended around it. Then this is attached to a rigid plate. The rigid plate is surrounding a block which is fixed to the ground. A total traversable displacement given by capital D. Further, the rigid weight is accelerated to fall down using some sort of a rubber band or spring. This is my weight W. This is being dropped. This is my thin wire for the one carbon device. Sorry. So this is carbon device. This is the rubber band rigid plate. Here we have the initial setup uses annealed copper as the thin wire, and when the weight falls down on the rigid plate, it imparts it with a velocity v1. So my rigid plate, this is the weight. This is my thin copper wire. So at this is x equals 0, and at x is equal to small x, let the displacement be u. So there is a tensile wave. The thin wire is being elongated, so a tensile wave is generated which travels upwards. And here we assume that the weight falls with a sufficiently high velocity v1, which is not slowed down. So I should write this as initial position upon impact. This v1 velocity remains constant throughout. This is what we assume. So to justify this assumption, what we would have is typically the weight is sufficiently heavy, and the rubber band or the accelerator, the rubber band or the spring is strong enough to quickly impart it with a high velocity, and because of its massive inertia, it just drops on the rigid plate and then traverses this whole distance d. So this v1 is the velocity at x equal to 0, and if we quickly consider a thin cross section with an area A naught and density rho. This thickness is dx. Then using Newton's second law of motion, what we find is small force dF accelerates the small mass dm into the acceleration. So dou square u by dou t square. Df is nothing but sigma d sigma into a naught. So change in stress across the small section. So rho naught a naught dx dou square u by dou t square. This should be partial derivative. So a small particle mass being accelerated due to imbalance of contact forces, which is basically the stress. And from this we get the equation d sigma by dx is rho naught dou square u by dou t square. We can write this d sigma by dx. Sigma is equal to E epsilon for uh, this is for uniaxial uniaxial stress in the elastic limit. Otherwise, we can write it as sigma is equal to sigma of epsilon. This would be valid for uniaxial stress, but also for the plastic limit. Sorry, also in the plastic range. So d sigma by dx we can write as d sigma by d epsilon into partial derivative of epsilon with respect to x, because strain can vary both as a function of position and time, which basically substituting this in this equation gives us dou square u by dou t square is d sigma by d epsilon upon rho naught into dou square u by dou x square. This is the plastic wave equation. So we end up with plastic wave velocity as V plastic is square root of d sigma by d epsilon upon rho naught. This d sigma by d epsilon in the elastic limit, we know it to be capital E, which is the Young's modulus. So basically this analysis that we have done, which assumes like a constant cross section and uh, which assumes constant cross section and the same density as no change in density. Rather, we can use the same analysis to obtain again the elastic wave equation, wave speed equation. Now, specific to the von Karman Duves experiment, what we see, we'll write down the boundary conditions. Just draw a diagram here. This is the rigid plate. This is capital X. Here, what we'll see is there is a so here what we'll see is x equal to 0. There is a longitudinal wave, tensile longitudinal wave traveling, and it has two wavefronts. There is an elastic longitudinal wavefront, and then there's a plastic longitudinal wavefront. Write this as ELW and PLW. The boundary condition at x equal to 0. This is the rigid plate which we know is traveling at a velocity v1. And this would be somewhere here would be the weight. Just draw that in a dashed manner. Right. So at x velocity, displacement u at x equal to 0 and time t simply v1 into t. We are assuming v1 is constant. Right. And another boundary condition is u at x tending to infinity for all time is 0, which means that the other end of the rod is fixed. It's fixed. So the top end of the rod we have already seen in the diagram is this is fixed here. So that displacement of the top end of the rod is 0, whereas displacement of the bottom end is given by V1 times T. If we rewrite this into three different regions and label them as region 1, 2 and 3, we get for each region for x between 0 and C1T. C1 is you have constant strain epsilon 1. This C1 is plastic wave velocity. So once the rigid plate starts moving, it will induce a strain equal to epsilon 1 in the section that is, it will induce a plastic strain, and that plastic strain will have a constant value. Maximum value of the plastic strain will reach some value, say epsilon 1, and that is what we are assuming will be constant throughout the region 1. Between then ahead of the region 3, which is the elastic wavefront, you will have uh, because there is no deformation, sorry, no disturbance has reached ahead of the elastic wavefront, there will be no deformation. So for the region 3 we can write x greater than c naught t, we can write epsilon equal to 0. And then for region 2, uh, so region 1 has the maximum total strain epsilon 1, which contains both elastic and plastic part. Region 3 is strain free, and region 2 falls somewhere in between. So it will have a velocity, it will have some deformation between 0, some strain between 0 to epsilon 1, and the exact value for a particular strain would depend on what, like we can write the relation between exact location and time to be in the plastic wavefront velocity d sigma by d epsilon upon rho naught. So for each point in the region 2, you could have like different sections with different epsilon values, corresponding to which you are calculating d sigma by d epsilon and then rho naught. So we have seen in the previous class that the elastic wavefront and plastic wavefront, if you have two of those, they spread out with time. So if I'm to draw, suppose I draw x by t, this is c naught, this is c1. C1 is the plastic wavefront corresponding to maximum strain epsilon 1, maximum total strain epsilon 1. So total strain means both elastic and plastic values. So x by t c naught, this is the elastic wavefront, and then you'll have different velocities depending on all the intermediate strain values going from 0 to epsilon 1. This is epsilon, this is x by t, this is my elastic wavefront. For x by t greater than c naught, this is the unloaded region, so this would be region 3, and for x by t less than c1, this would be region 1, which is maximally strained region, and in between here you have region 2, c1t less than x less than c naught t, where x by t is given by square root of d sigma by d epsilon upon rho naught. And if I plot the wavefronts at two different times, this is x, epsilon t is equal to, I'll plot them on the same value. So this is moving ahead with C naught, this is moving ahead with C1, and this is T is equal to T1. I plot another value, C naught, C1. This is the maximal strain epsilon. So there is a spreading out of the wave. You can see here that this distance is much larger than this distance. So the wave is spread out. This is basically the this is the dispersion nature. So we see a dispersion here, and now we are interested in doing an analytical treatment of the same. So if we want to find the maximum strain, so we wish to find maximum stress sigma 1, which is your flow stress, and maximum strain epsilon 1 undergone by the wire at some impact velocity v1. So we first have, so this is what we wish to find, sigma 1 and epsilon 1 at some impact velocity v1. So we'll first write down the boundary condition. U at x is equal to 0 is v1 into t. And if I look at a small thin cross section with length dx, your change in force can be written as, or rather the differential in force across the two sections can be written as df. Should write this increase in force is change in area into sigma naught, and this basically will, this force increase will travel the distance dx in time dt. So what does this mean? Your plastic wave is moving forward, so it will have a wave front, and the change in stress will move at a certain velocity given by the plastic wave velocity that we found previously. So we are trying to quantify how much uh, how much time it takes for that particular stress wave at some stress sigma to travel a small distance dx. So we can write plastic wave velocity at stress sigma naught as Vp naught equal to dx by dt. So here I should write sigma naught plus sigma naught, and this should be sigma naught. So sigma naught and sigma naught minus t sigma. So this sigma naught stress, that increase in stress that we are seeing due to the tensile loading, will travel the distance dx in time dt, and that will be basically the plastic wave velocity corresponding to that stress sigma naught. And we know that this plastic wave velocity is given by square root of d sigma by d epsilon at stress equal to sigma naught divided by the density. So assuming we assume constant like sorry, we assume constant density and area here, cross section area. So this is what we have. Just if I'll just write down this in a slightly different manner. D sigma naught by d epsilon upon rho naught. Okay, if I now use conservation of momentum for the small mass, for the small mass dm is equal to rho naught a dx, and your change in the velocity of the small mass is given by change in force to time. So like the net impulse that this increase in force provides over the time dt will lead to a change in momentum for the small mass. So I'll carry this on to the next page. So you have rho naught a dx, which is the mass, into change in velocity is area times d sigma naught, which is the change in force, increase in force, and time dt. If I move things around, remove out the area term, what do I get? dv is equal to d sigma naught upon rho naught into dx by dt. This is nothing but plastic wave velocity at sigma naught. So dv is equal to d sigma naught by rho naught square root of d sigma naught by d epsilon upon rho naught. I move this around. dv, if I integrate this rather, what do I get? Integral dv is integral 1 over rho naught d sigma naught upon vp naught. It's nothing but this integral dv, if we take v1 is at x is equal to 0, so you have got v1, and the other end is root of 1 by rho naught d sigma naught plus square root of rho naught will come above root of d sigma naught by d epsilon. So you get square root of d sigma naught d epsilon by root of rho naught. And if we change limits, so initially our limits are sigma going from 0 to sigma naught, or sigma 1, sorry, the maximum stress. Sigma going from 0 to sigma 1 is same as the strain epsilon going from 0 to maximum strain epsilon. So we can write V1 is square root of 0 to epsilon 1 root of d epsilon d sigma naught by rho naught d epsilon squares into d epsilon. This is integral which gives us the expression V1 is integral 0 to epsilon 1 square root d sigma naught by d epsilon by rho naught d epsilon. So this is what the generic equation would look like. And now what we have is, so this is the general solution. From Right. So we have now found a relation between the impact velocity v1 and the maximum total strain epsilon 1 that the annealed thin rod will achieve upon the impact of that weight. You can see from this equation that the d sigma naught by d epsilon term in the numerator of the square root is not a straightforward term to calculate, and it would depend on the exact form of material constitutive relation that we have. Recall in the previous class and previous week's lecture, we have looked at different types of constitutive law, such as the bilinear elastoplastic. Then you also have your power law constitutive equation and stuff like that. So based on each particular constitutive law, you could do a numerical integration wherein if you have the experimentally available data, you could figure out the numerical derivative d sigma by d epsilon at each value of strain upon, and then take the density as constant and then integrate it for each incremental strain value. So I think I suppose you guys are a bit familiar with numerical integration techniques. If not, there is a good book called, I think, Chapra and yeah, there's a good book called as Numerical Methods for Engineers by Chapra and Kanal. So could refer to that. That's a good starting point. So if we assume some sort of, if we assume a power law, say sigma is equal to a epsilon raised to n. From this, then we can calculate dou sigma by dou epsilon is equal to k n epsilon raised to n minus 1. An example of power law could be for, so like for, I think for polycrystalline copper, the relation between true stress and true strain can be given using power law, which takes k is equal to 800 MPa and n is equal to 0.2. So this could be, say, no, sorry, 0.4. I'll check the exact value one second. But the idea is that if we have a relation like this, we could easily evaluate dou sigma by dou epsilon, and then your integration becomes straightforward. So v1 is square root of 0 to epsilon 1 root of d sigma naught by d epsilon by rho naught d epsilon, which is 0 to epsilon 1 square root of kn by rho naught epsilon raised to n minus 1 by 2 d epsilon, which is kn by rho naught square root of kn by rho naught 2 by n plus 1 epsilon 1 raised to n plus 1 by 2 v1. So this could be your maximum, this could be your relation between impact velocity and maximum strain, from which you can write maximum strain is n plus 1 by 2 whole square rho naught by kn v1 square whole raised to 1 by n plus 1. This is the maximum total strain. You could in turn, sorry, you could in turn evaluate what stress sigma 1 is sigma 1 of epsilon 1. You could use this constitutive relation to figure out the maximum stress that the uh, thin wire will experience. One of the limiting criteria for this is that if we if we draw the engineering stress strain curve and the true stress strain curve, this is the true stress strain curve. And if I take first derivative of dou with respect to sigma, the point where it intersects is called as is the necking point, and we obtain this using considers criteria. So considers criteria is uh, used to evaluate the necking instability, and it's very simply done. Sigma is equal to true stress into the current area, and if we do dP, which is the change in force, is 0, d sigma A plus sigma 2 dA. From this we can evaluate change in d sigma by sigma 3 is minus dA by A, which is nothing but dL by L, assuming constant volume. So we can assume constant volume till the necking instability, beyond which there will be some increase in volume. So the true stress strain curve, if we ever draw it, it has to be only considered till the necking point. So we will not look at the region ahead of it. And from this relation, we can figure out that this is nothing but the true d epsilon 3 increase in the true strain, which gives us true stresses d sigma transpose by d epsilon transpose. Sorry, d sigma 2 by epsilon 2. This is my considers necking condition. And if for a lot of metals, we can write sigma t is equal to k times epsilon t raised to n. So the engineering stress strain curves that we have seen before, they can go like this. You have an elastic region, then you have a yield point, a plastic region, a necking point, and so on. This is my engineering curve. But at the same point, you can draw a true stress strain curve. So a lot of times the true stress strain curve can be represented using a power law, which is what we have written above. And find out once I find out this, assuming sigma t is k epsilon e raised to n, you have, which is n times k epsilon t n minus 1, which gives us epsilon t is equal to n. So this is the maximum strain at necking instability. If I put this maximum value of strain into my original equation, I get the maximum permissible velocity as root of k over rho naught n into n plus 2 by 2 upon n plus 1 by 2. This becomes my maximum permissible velocity, maximum impact velocity at necking instability. It could, our power law will work the way we have defined it. It will work. You could define true stress and true strain ahead of the necking instability, but the power law relation that we have obtained k epsilon raised to n, we typically have it till the necking point. So if we assume that as, say, my point of failure for the material, this is the impact velocity that you have. You could in theory also have some other criteria. Sometimes people prefer to not have yielding or have like no plastic flow, only be the material should only be in the elastic regime. If that is the desired criteria before calling, before we say that your material or structure will fail, then you can use that particular value of strain and plug it into your impact velocity relation, which that we have obtained here. So that gives you maximum permissible velocity. You could say for this sort of values, you could figure out what the maximum velocity looks like. Would be square root of 800 10 raised to 6. Suppose the density, I'm taking any value. So 2700 typically corresponds to aluminum. I'm just writing it down. And you could have zero point 0.4 raised to 2.4 by 2, so 1.2 upon 1.4 by 2, so 0.7, something like this in meter per second. Thank you, 2700. Okay, so this quite high velocity. Okay, the next part of this week's lecture was on two simple, two experiments relating to how do we generate plastics, how do we generate plastic waves of combined stress. So the first experiment was Lipkin and Clifton. So what do we mean by combined stress? We basically have longitudinal wave and shear wave. So shear stress and longitudinal stress. In longitudinal, your particle velocity is parallel to your wave front, whereas in shear, your particle velocity is perpendicular to your wave front velocity. Here, we are looking at, yeah, go ahead. Go on. Ask.
Sir, could you hear me? No?
Sorry. Yeah, I can hear.
Yes, sir. In previous derivation,
Hmm.
von Karman and Dewey's experiment,
Hmm.
we are considering that area is constant throughout the rod, but it is the plastic wave.
Hmm.
So why we won't consider that the area changes in that derivation, sir?
So in this analytical treatment, we are not looking at changes in area, but you could have like in Taylor's experiment, for example, we do have a change in area also being accounted for.
Okay.
So
Maybe
hmm,
it's a form of a thin rod. It's negligible in size that we won't consider, or any
so
other specification you
the
have there.
that is part of it. Like the radial inertial effects are ignored anyways. But I think like your doubt is, I feel your doubt is relevant because I was also looking at it for the past week or so, trying to understand. In some in some analysis, they do consider like say the rod is being like there is a change in area associated. Like you have like a plastic wavefront, and then you have an elastic wavefront. In between, there is some changes in area, cross section area. So there are some analysis to do that, but in this particular uh, analytical treatment, we have assumed it to be constant.
Okay, okay, sir. Thank you.
As I think in the Taylor's experiment, we assume it to be, sorry, in Taylor's experiment, we explicitly account for change in shape of the finite thin rod. So that is basically like there's a ballooning effect, and then later on, if the impact velocity is very high, things will start mushrooming.
Okay, okay, sir.
Uh, so the first experiment for the in combined stress is the Lipkin and Clifton experiment, where you have like a striker bar inside a pressurized gas. This is my transmitter. This is my striker bar. This is my specimen. So specimen is a thin, hollow tube which is being held by a rear mount assembly, so RMA rear mount assembly, and it is held at a, it is torqued. So there is a torque applied. So there is a torsion applied which exceeds yield point. So there is already some sort of strain energy being stored in this hollow tube, and then you have an impact where striker hits transmitter, which in turn hits specimen. So the striker bar hits with a sufficiently high velocity, which basically produces a plastic longitudinal wave due to impact, and plastic shear wave due to initial torsion from our end. So both of these are generated, and then we try to record them to understand material behavior at different strain rates. An easier, uh, slightly easier example is this Clifton's group's experiment, wherein you have a I think it's also called as the oblique plate impact. Here you have a target, you have a, this is my impactor, this is my flyer plate. It's in a pressurized barrel. This is Sabot, also projectile. This is the barrel. This moves ahead with the velocity v. Again, you have your flyer plate, which is parallel to the target, but not perpendicular to the impact velocity, which is why it's called as the oblique plate impact. When it hits the target, different waves will be generated. We have already seen, I think, in the second week's lecture, that what happens when you have uh, different, sorry, inclined media coming, sorry, not inclined. We have already seen that what happens when you have two medium coming together at an interface, and what sort of waves will be generated. So here you'll have at least, say, like three different wavefronts. You can have like a shear wave, which is elastic with particle velocity like this. You can also have uh, plastic shear, plastic longitudinal wave, elastic. Elastic, elastic longitudinal wave. You can also have draw this. This is my target. This is my flyer plate. You can have a. This is the wave front. This is the particle. You can have another wave fronts. You could have like a elastic longitudinal wave front. You could have like a shear elastic wave front. You could also have a plastic longitudinal wave front. This is my target. This is my flyer. You could similarly have different wave fronts in the flyer plate. And if impact velocity V1, V1 is high enough, you could also have plastic shear wave, SP, so plastic shear wave. So again, like I think this setup is quite easy to understand. At the point of impact, you will have normal force. You'll have different stresses coming together. So you'll have say like a normal force and a shear force being applied to both the plates simultaneously, which will in turn result into normal stress and shear stress, which will propagate in both flyer as well as target. Depending on the exact amplitude of stress that we have, you can have plastic waves also being generated for both the longitudinal and shear waves. And yeah, okay. Next, I think this is perhaps the most important part of this week's lecture, which is Taylor's experiment. These are performed around World War II, and they were interested in seeing understanding plastic deformation. And the way it was done was using a rod with a finite length, imparting it with a sufficient high velocity, and impacting on a rigid plate. So you had you had a finite rod going with velocity u with an initial length L, impacting rigid surface. I'll call this step 1. Step 2 is at impact, plastic deformation will happen right after the impact. There will be, so this free end is still traveling with velocity u. There will be an elastic wavefront generated with a velocity ce. There will be a plastic wavefront generated with velocity cp. So both ce and cp are compression waves. I'll call this region R1, and we'll refer back to the region later on. Then you have said another snapshot wherein your elastic wave has reached the free end, which is the left end. There is an increase in deformation on the right hand side. You have a shape change coming up, increase in area. This is CP. This is CE. This I wrote this as C. The free end is still traveling velocity u. So your release wave, which is tensile, coming back from the free surface. I will call this as the region 3 R3. I should call this as the region R2. Then your released tensile wave will interact with your uh, incoming plastic wave deformation. So that will cause stress to go to zero, and that would in turn lead to interaction between release wave and plastic wave. This will lead to stress becoming zero, which in turn would lead to end of deformation. You could draw a couple of more stages in between for this finite bar case, and that could tell you about how the exact deformation happens. Like between snapshot 2 and 3, you could have a region where elastic wave is about to reach the free surface and the plastic deformation zone has increased. Similarly, between 3 and 4, you could have another stage where the release elastic wave is yet to reach the incoming plastic wave. Suppose I now draw this. I'll write this is capital X L1. Suppose I now draw schematic. This is velocity u, initial area A naught. This is the plastic wave front, velocity v. This is the final area A. Somewhere in between, you have the elastic wave front with velocity c. So if I zoom into this part, you have a section where area is almost constant velocity c and velocity v. Using conservation of mass, we can see that this interface I, there is some amount of material entering this interface, which is material entering with velocity v, and sorry, exiting with velocity v on the right hand side, and material entering with velocity u minus v, so like relative velocity, which is u plus v. If I apply the conservation of mass, rho naught a naught into u plus v, which is the entering of the material into the interface I, is same as rho a into v. If we assume rho as rho naught, so later on when we go into shock waves, we'll have cases where we also account explicitly for density changes. But for here, we can assume same rho equal to rho naught. Then you basically have a into v is a naught times u plus v. So capital U. So this is the first equation. Next is I'll draw a small section on the interface. So here you have area A, then area A naught, density rho, density is same rho naught and rho. This is the small section. I assume like a constant area. This is my small thin section with length dl. We can write dl as the amount of material undergoing plastic deformation in time dt. So this is basically the material that will cross the interface I from the left hand side, which gives us dl will be u plus v times dt. And the mass can be written as rho naught a naught dl. So dl is entering from the left hand side. We will take the area according to that. So you have got rho naught a naught u plus v times dt. Another thing that we assume is on both ends of dl, you have dynamic yield stress sigma yd acting. So these Taylor's experiment were conducted specifically to understand what sort of dynamic yield stress you have, uh, what uh, what dynamic yield stress a material has, and what sort of impact velocity the rod goes with, and based on these two factors, what amount of total deformation you see in the material, which is quantified using strain term. So if sigma yd acts on both sides of the small section dl, the change in force would come primarily due to the change of area that the section goes through. So you can write your force as minus, so it's a compressive wave load, so minus a naught into sigma yd. It's minus sign for the compressive, which is nothing but the small mass dm into acceleration. So acceleration is write as a, right? And what is the acceleration? What is this acceleration a? dl initially was moving with velocity u, and after time dt it became stationary, which means that our acceleration is nothing but minus of 0 minus u by dt. So if I use this equation and this equation together, I have a minus a naught into the dynamic yield stress, change in area into dynamic yield stress, is equal to u by dt rho naught a naught u plus v. Right. So we will also use this equation here. I'll write this as equation 1. From 1, this is equation 2. From 1 we know that u plus v is, sorry, a naught u is a minus a naught times v, which means v is a naught u upon a minus a naught, which gives us u plus v is av by a naught. which is A by A naught times A naught U upon A minus A naught. Right. So once we plug this equation 1 into 2 and simplify it, what we end up with rho U square is A minus A naught square by 2 into A naught into yield stress. And if we assume constant, sorry, so here we have change in cross section area, but we still have constant density, and we also have the constant mass, which basically gives us, rather the constant density part, using mass conservation, if you have constant density, you basically have a constant volume condition. So if the initial length was L, L naught A naught, the final length is LV, L into A. This is my original area, this is my changed area. And if the initial length was L naught, or say DL naught, there is the final length now becomes DL. So you can write strain is 1 minus L by L naught, nothing but 1 minus A naught by A. If I plug this, if I plug this relation into this one, we end up with rho U square by sigma yd is equal to epsilon square upon 1 minus epsilon. So this is a very simplistic analysis, and from this what we get is, so a lot of assumptions have gone into this. We have assumed like the we have assumed constant density, so like the stress is high but not so high that there are changes in the uh, changes in a small infinitesimal volume. We have also assumed that there is some dynamic yield stress sigma yd, after which acts on the interface, transforming a material moving with some velocity u into bringing it to rest with some sort of permanent deformation, and that gave us this form of relation, rho u square by sigma yd is epsilon square upon epsilon minus 1. And now we look at the particle velocities. So we have already seen like three different regions, R1, R2 and R3, R1, R2 and R3. For the region R1 where the elastic wavefront is still yet to reach, you will have simply the velocity, particle velocity up is equal to u. Region R1, this is ahead of the elastic wavefront, so particle velocity up is nothing but u. If we take region R2, region R2 lies behind the elastic wavefront, so there will be some uh, there will be some so there will be some stress, so the stress wave will be traveling and there will be some sort of particle velocity associated with it. If we look back to our previous relations, you have sigma yd upon c2, not c being the c being the wavefront velocity at that particular stress inside the region between elastic wavefront and the plastic wavefront, which is moving ahead and deforming the material to rest. Once the elastic wavefront hits the free surface, there is a change in the there is a change in the there is a release wave a tensile release wave originating from the free surface which comes back, that causes the stress value to invert, but the particle velocity still has the same sense. So you have your reflected wave and incident wave particle velocities to be same. We have already seen this in the second week's lectures where we saw what happens when you have a longitudinal wave interacting with an interface between two materials with two different sonic impedances. So this particle velocity is increased to twice of that, which gives us for the region 3 particle velocity being u minus. So now I divide 1 0 c. So three different regions have three different particle velocities, and the final part is how do we uh, evaluate the total deformation length. So this we call this elastic wave C. Here we have deformation, then a plastic wave V, rigid surface moving with velocity u. This is x. This is interface I. This is region H. This has area A. This has area A. So we write that if we think of the time taken for the elastic wave to travel from interface I to free surface and back, okay, dt is equal to twice of this distance x by the elastic wave velocity c. We also know that increase in plastic region given by dh is v times dt. V is the plastic wave front velocity, which gives us dh is equal to v times 2x by c. So at any given point, increase in the elastic wave front, increase in the plastic region can be related to the uh, non-plastically deformed region x, rather the distance of the elastoplastic interface from the free surface x, and the elastic uh, wave velocity c and the plastic wave velocity v. We look at this is one relation. We look at how much time this takes. So the plastic region advances by dx during time dt 2x by c. So we have got dx is minus of u plus v, which is the relative velocity on the left hand side of the material on the left hand side moving inside the elastoplastic interface I. This is mass going into interface I times the time, which is 2x by c. And what you have is there is also a change in impact velocity. So there is also a change in impact velocity associated cu minus sigma yd by c rho naught, which is the incoming wave, and then the release wave. So if I combine this with the time relation, we have got dh by dt is equal to v. This is basically the definition of plastic wave propagation. And change in area dx by dt is minus of u plus v, and change in u by dt is minus 2 sigma yd by c rho naught into c by 2x, which is minus sigma yd and rho naught x. So this refers to decrease in impact velocity of the projectile. Using mass conservation, you have got a naught into u plus v ab, which gives us v is equal to a naught u upon a minus a naught. If I rearrange this terms 2 times a naught by a upon 1 minus a naught by a. This is nothing but your strain term denominator, so u into 1 minus epsilon by epsilon. What v is 1 minus epsilon by epsilon times u. So this is a plastic wave velocity in terms of impact velocity. You do change in dx by du, which is dx by dt upon du by dt, can be written as u plus v rho naught x by sigma yd, which is nothing but u rho naught by sigma yd using this relation u by epsilon times x. So you have got dx by x. Dx by x is rho naught u by sigma yd epsilon du. Taking this to the right hand side and this on the left hand side. I'll multiply the this side with x and x. So you have got 2x dx by x square, and you have got rho u naught square by d of multiplying both sides by 2. So 2 rho naught u 2 u du by sigma y into 1 by epsilon. This term is nothing but d of rho naught u square by sigma yd, which we have seen is d of epsilon square upon 1 minus epsilon. It's the final deformation. So on the left hand side you have a term which d of x square upon x square is 1 over epsilon d of epsilon square upon 1 minus epsilon. So integrating you get ln of x square integral 1 upon epsilon d of epsilon square upon 1 minus epsilon, which is epsilon square upon 1 minus epsilon 1 by epsilon plus integral epsilon square upon 1 minus epsilon d of 1 over epsilon, which is minus 1 by epsilon square. This should be a minus 1 by epsilon square b epsilon. Minus minus would become plus, and you have epsilon upon 1 minus epsilon plus minus 1 upon 1 minus epsilon minus d epsilon can be written as d of 1 minus epsilon. So you end up with ln of x square epsilon upon 1 minus epsilon minus ln of 1 minus epsilon plus some constant k. And boundary conditions, if I look into them, this is my x, so at, and this is my L. So boundary conditions are at x is equal to x, you have epsilon equal to 0, which is this front, and at x is equal to L, you have epsilon being epsilon 1, which is the maximum strain. So if I plug this into this, I get ln of x square by Ls square is 1 minus 1 upon 1 minus epsilon 1 plus logarithm of 1 minus epsilon. This is what my general solution looks like. But we already know that rho u square by sigma yd will be epsilon square upon 1 minus epsilon 1. So which means we can write L1 by L and x by L as functions of, so both L1 by L and x by L1 by L and L is the original, both L1 by L and L by L, x by L can be written as functions of strain epsilon 1, which in turn can be written as function of rho u square by sigma yd. So why this rho u square by sigma yd? It's because it becomes like a dimensionless parameter to compare different kinds of uh, boundary conditions. So if I draw rho u square by sigma yd, dynamic yield strength L1 by L 0, 0.2, 0.4, 0.6, 0.8 and 1, you have L1 minus x by L, which is the, so L1 by L is the final deformed length. L1 minus x by L is the deformed, sorry, plastically deformed region. So you get something like this for L1 by L, something like this for L1 minus x by L. And if you check with the experimental values, they go something like this. So from Taylor's analysis of the experiments, we get that when rho u square by sigma yd is small, particularly say less than zero point 0.5, then you have a good match with experiments. And the reason is that if you look at experimental snapshots, you have small deformation coming here, and rho u square by sigma yd. This is the dimensionless parameter. Suppose it's zero point 0.5, something like 1.3, it becomes like this. And at very high values, say like 3.6, there is a big change in shape. So this is also called as mushrooming effect. So sometimes you can even have a, sorry, sometimes you can even have like a concave shape if the impact velocity is very high. Like instead of this convex, you could have something like this is how impact and some material flows outside. Okay, so uh, right. So depending on the values of say rho u and sigma yd, you could find out what your analysis looks like. So suppose you have rho is equal to 2700 kg per meter cube, u is 200 meter per second, and sigma yd is say 800 MPa. Then if I calculate my dimensionless parameter, 2700, so 2.710 cube, 200 is square is 4 into 10 raised to 4 on 800, which is 8 into 10 raised to 8. So this is 10 raised to 1. So 2.74 is 10.8 by 80, which is approximately 10.8 by 80. Right. So for this particular value, you can clearly see that this is less than zero point 0.5, which means that if these are the parameters that we know, dynamic yield stress, impact velocity, and density, then you can use whatever assumptions that we have done in this analysis. You can use those assumptions are valid, and after impact, your predictions from this simplistic analysis will match with should be close with your experiments. If say for whatever reason we decide to raise the velocity to say 400 meter per second, say 500 meter per second, then you would have 2.7 rho u square by sigma yds, 2.7 into 25 upon 80, which is 6, just 67.5 upon 80, which is much sufficiently greater than zero point 0.5. So there will be some amount of shape changes associated, and your analysis will start falling away from uh, the experiment. So yeah, this is what I had for this particular session. Uh, if you have any doubts on any of these and whether the tailors are, sorry, if you have any doubts on this analysis or yes, go on.
Yes, sir.
Hmm.
So my doubt is,
Hmm.
in region 3,
Huh.
we are multiplied that two times of the particle velocity,
Hmm.
right, sir?
Yes.
So, so actually, the
Hmm.
compressive waves travel to the free surface. So
Hmm.
after reflection,
Hmm.
how does it get double the value, sir?
So when when you have like a free surface, what happens here is like suppose the particle velocity compressive wave, initial particle velocity is up. What happens on the free surface is that the reflected particle velocity up up reflected by up incident. This is what they are both same, whereas reflected stress by incident stress is -1. So this is how the release wave comes out. Compressive wave is the incident wave, and then the release wave will be tensile wave. But the reflected particle velocity is same as the incident particle velocity. So at the free surface, those two waves kind of get superimposed. This is my incident wave at t is equal to t1 going, and there is some velocity with velocity u. as we reach the free surface, let this be my particle velocity UP. At t is equal to t2, when the wave will reach free surface, you will have both particle velocity being superimposed. So UPI and UPR are in same phase, same sense, and sorry, same phase, and get these two basically get superimposed. When the superposition happens, you would have technically you have two waves. I'll draw the other one with green. So my green is reflected reflected wave, whereas my red is incident wave. This is a plot of particle velocity. So both of them get superimposed, and that basically leads you to the overall particle velocity being twice of UPI. This, this.
Oh, got it, sir. Thank you.
So because of the superposition, this happens. So like I like part of my PhD problem is basically on wave propagation and structure. So when we do an analysis like this, like if you hit a rod with some velocity and take a very low impedance material on the right hand side, which which mimics the free surface effects, then at the uh, at the free surface, very close to the free surface, if you look at the particle velocity, it becomes roughly twice as much of your initial particle velocity. Then the reflected wave will travel backward. It will be a tensile wave with some velocity, but at the interface or very near to it, you will have double as much of that. Okay.
Yes, sir.
Hopefully this
And I got it, sir.
makes
Thank
sense.
you.
Okay. Uh, yeah, then I think if this is the only doubt, then we can stop this session. Yeah, thank you for attending. I'll see you again in the next one.